So the main idea so far of this unit has been that light is a particle. Okay? Well, a guy comes around by the name of DeBroglie or DeBroglie and basically says, what if the opposite was true? What if the opposite of that was true? In other words, what if particles are also waves? In other words, if waves can be both particles and waves, what if particles are really actually both particles and waves also? Okay, so that was kind of DeBroglie's proposal. He said if this was true, then they must have a wavelength. And we're essentially going to take that last equation, the momentum of a photon, flip it around, and say, well, there must be a wavelength of a particle, and we could write that as lambda equals h over p. Okay, so lambda would be known as the wavelength. Should probably shrink this. Oh, it's not going to let me. Lambda is a wavelength, and then h is, of course, Planck's constant, and we're going to use the Joule version. And then what is p? What's the momentum? And what's our equation for p? Remember from the first semester, momentum equation? Just mass times velocity, right? So it'd just be kind of proportional to this. Alright, so anyway, that was DeBroglie's proposal. Of course, people didn't really take it seriously at first. Because, well, let's just do a real simple example problem. Let's find the wavelength of like a person, like a human, someone going for a jog. That means, according to DeBroglie, they must have a wavelength. So someone going for a jog must have a wavelength as they're making their little run, if they're doing their little run. So let's see what it would be. Get some perspective. So what is the wavelength of a 70 kilogram person jogging (5 meters per second). Okay, so why don't you go ahead and do that calculation. The math is not hard on this unit. I mean, it's pretty much just plugging things in. The concepts are the difficulty, knowing what's what, when to plug in for what problem. So what's the wavelength of this average guy going for a jog?
1.8 miles times 10 to the 36.
So what do you notice about this number? It's extremely small, right? And so, you know, practically speaking, you couldn't see this. Even if DeBroglie was right, how would we confirm this? Because you can't see these kind of tiny wavelengths, right? You wouldn't see this this vibration or this movement of the wavelength. Now, how could we test this? What could be an experiment we could maybe do to prove that particles were waves? What was the experiment that proved that light was waves? The double slit experiment. So perhaps we can construct a double slit experiment with people. Okay, well, we have people running through double slits and somehow canceling each other out or constructively interfering with each other to create regions of lots of people and no people. Okay, now the problem with using people in our experiment, okay, is what were true about this kind of the sizes of these slits. Yeah, they were small. They had to be on order with the wavelength. So with sound that has a very large wavelength, we notice this effect all the time. With light, we have to get really small slit distances, and this would have to be even smaller, like 10 to the negative 34th or something like that, slit spacing, which would be ridiculous. I mean, we'd slice ourselves up, right, if we try to go through that kind of slit. So what do we do then? So we obviously can't use people. Well, look at our equation. Let's get some more reasonable wavelengths. So to do that, we want our wavelength to get larger, which means we can either mess with the mass or the velocity. Well, let's mess with the mass. Why don't we use a really small particle, such as an electron? Yeah, why don't we use an electron? And that's what a couple of gentlemen did. Okay, this was called the Davison Experiment. Actually, I think it's with an M. Forget. So essentially, and they did this with gratings, but I'm going to just model it with a double slit because the concept would work. The concept is the same. So if we were to send some electrons through a double slit, if electrons were truly particles and only particles, what would you expect back here on our wall? You would expect a bunch of electrons right here and a bunch of electrons right here. Right? Right in front of the openings, just like if these were machine guns shooting through two openings, you expect to find a lot of bullets right here and a lot of bullets right here. Okay? However, when they did the experiment, what do you think they found? So this would be if light was a particle. If particles were particles. But if particles were waves, you would expect to see what they saw. And this is what they saw. They saw a bunch of electrons located right here. So right here there was a high number of electrons. Right in the middle, right behind the barrier. And then they found these regions of alternating amounts of electrons. So high numbers right here, this would be low, this would be high again, and vice versa. So somehow these electrons were canceling each other out in some regions, and other regions were basically constructively interfering, or so to speak. Okay, so this is kind of the evidence. So on a test, if they ask you what's the evidence that particles are also waves, you would refer to this experiment, okay, a double slit, or they actually used a grating type experiment to produce this interference pattern. Okay? All right, so let's go ahead. So wave-particle duality that we've been talking about, this expands to everything. So in other words, not only are waves and particles, like light is a wave and a particle, but particles are also waves and particles. So they're both. So wave-particle duality expands to everything. Essentially everything is both.